Hi everyone and welcome to Lesson 3, Video 1, Heat and Temperature. There will only be one video for Lesson 3. This video is the beginning point for your studies of thermodynamics. By the end of this video, you should be able to use the kinetic theory of matter to describe matter as consisting of particles in constant motion. By the end of this video, you should be able to describe all substances as having internal energy due to the motion and separation of their particles. And you should be able to define temperature as a measure or representation of the average kinetic energy of the particles in a system. Thermodynamics is the study of the movement of heat. Thermo meaning hot or heat or temperature, and dynamics meaning to move. Thermodynamics is the physics of heat, temperature, energy, and work. As we begin our studies of thermodynamics, it is a good practice to link it back to ideas and concepts that we've been generating our whole lives. From as far back as most of us can remember, we've had these concepts of hot and cold. Some things are very hot, while some things are very cold. And then again, some things are just warm. As we said in previous lessons, we like to measure in physics. We like to quantify so that we can communicate meaningfully with other physicists and scientists around the world. In short, we ask the question, how hot is hot? How cold is cold? And how do we compare different objects for their hotness or coldness? To be able to compare one object to another in terms of hotness or coldness, we use temperature. Temperature provides a scale for comparison. The earliest temperature scale is the Fahrenheit scale, invented by the German-Dutch scientist Gabriel Fahrenheit. Gabriel Fahrenheit created his Fahrenheit scale by taking a water, ice, salt slurry and making that 0 degrees Fahrenheit, and then saying that 100 degrees Fahrenheit is the average temperature of a human body. In Year 11 physics, we will not be using the Fahrenheit scale as it is not an SI unit. The Celsius scale. The Celsius scale was invented by Swedish scientist Anders Celsius. This scale is much more sensible than the Fahrenheit scale. It sets the freezing point of water as 0 degrees Celsius and the boiling point of water at 100 degrees Celsius. This is more sensible than the Fahrenheit scale because anyone on the planet can organize to have water at its freezing point, and also anyone on the planet can organize to have water at its boiling point. There is no chance for confusion over the exact mix of an ice-water-salt slurry, nor is there any chance for confusion over the exact average temperature of the human body. So anyone on the planet can create a Celsius scale. The Celsius scale, however, is also not an SI unit. The SI unit for temperature is Kelvin. In the 19th century, the Scottish engineer Lord Kelvin determined that when a gas is cooled to negative 273.15 degrees Celsius, its particles cease to move. You might remember from Lesson 2, when you completed the questions in Heinemann Physics Chapter 1.3, there was a graphical analysis question relating to the pressure of gases at different temperatures. This is very similar to what Lord Kelvin did in coming to the conclusion that there is an absolute zero of temperature. Lord Kelvin used this predicted absolute zero point of thermal energy to be his absolute zero of temperature. This then led to the freezing point of water becoming positive 273 Kelvin. The Kelvin scale is preferable to the Celsius scale because it is an absolute scale. That means there is no negative value for temperature in the Kelvin scale. It is useful to note, however, that while the Kelvin scale is the SI scale, the Celsius scale is still very useful for us in Year 11 physics, because the difference between any 2 points in temperature for the Kelvin is identical to the difference between any 2 points in temperature for degrees Celsius. As an example, the difference in temperature between freezing and boiling water is 100 Kelvin. Freezing water is 273 Kelvin, boiling water is 373 Kelvin. The difference is 100 Kelvin. At the same time, the difference between the freezing point of water and boiling water in degrees Celsius is 100 degrees Celsius. Water at its freezing point is 0 degrees Celsius, and at its boiling point is 100 degrees Celsius. I've said previously that in physics we like to measure, we like to quantify. And a temperature scale like Kelvin or degrees Celsius allows us to do this. It allows us to make observations of the world around us and to compare different bodies for their hotness and coolness in a way that other people can understand. The other thing that we like to do in physics, and which is also very important as a part of the scientific method, is we like to create theories explaining why the universe is the way that we observe it. One of the early theories to explain why some objects were hotter than others is the caloric theory. This theory, which was widely accepted in its time, suggested that there was a fluid which had no scent, no color, no weight, and yet was responsible for the temperature of an object. It was suggested in the caloric theory that this fluid existed between the particles of a material, and that a material was at high temperature if it had a large amount of caloric, while the material would be at low temperature if it had a low amount of caloric. When we observe one hotter material causing a cooler material to warm up, it was suggested in the caloric theory that caloric was moving or passing or pouring from the hotter object to the cooler one. It is interesting to discuss the caloric theory at this point because it is not a theory that we accept today. In physics, you will see that the theories we use are under constant scrutiny and will be improved upon as time passes. It's important to remember in physics that no theory is perfect. Rather, the theories that we use are simply the best understandings we have for now until evidence-based studies can improve them or provide better theories which are more close to the reality of the universe. Benjamin Thompson brought about an end to the caloric theory when he made observations which directly challenged and contradicted the caloric theory. He noted that when drilling a cannon barrel, heat would be generated even though the drill bit and the cannon barrel were both cold to the touch prior to the commencement of the drilling. This is direct contradiction to the caloric theory, which states that caloric must be present for there to be high temperatures. Neither the drill nor the cannon were hot before drilling. There was no caloric before the work was commenced. From this, a new theory emerged, the Kinetic Theory of Matter, the theory that we use today and will be using in our Year 11 physics studies. Thomson proposed that heat was produced by the motion taking place amongst the particles in the body. Particles that were later identified as atoms and molecules. The kinetic theory of matter exists upon a number of assumptions. The kinetic theory of matter assumes that all matter is made up of many very small particles, which today we know to be atoms and molecules. As an example, the particles of water are H2O molecules. The particles in the air around us are nitrogen molecules, oxygen molecules, carbon dioxide molecules, and a mix of other compounds. The particles in a rod of aluminium are aluminium atoms. The kinetic theory of matter assumes that the particles making up matter are in constant motion. In solids, they're vibrating about their fixed locations. In liquids, they're trapped in close proximity to each other, but they're free to move and slide around each other. And in gases, they're completely free from each other, moving in random motion in any direction allowable by the container with which they're in. The particles in the kinetic theory of matter move constantly, interact with each other and interact with the walls by way of elastic collisions. The kinetic theory of matter assumes that in any interaction between particles within a material or between the particles in their container, the total kinetic energy going into and out of that interaction is always conserved. No kinetic energy is lost or gained during elastic collisions between particles. The kinetic theory of matter assumes that there are forces of attraction and repulsion between the particles in a material, and that these forces are responsible for the different states of matter that we see in the world around us. Finally, the kinetic theory of matter assumes that the distances between particles in a gas are large compared with the size of the particles themselves. Having now introduced the kinetic theory of matter, and also having introduced temperature scales such as the Kelvin scale and the Celsius scale, I'll now wrap up this video by going through a number of the terms that we're going to use in our studies of thermal physics. The first term of interest is internal energy. In Year 11 Thermodynamics, we define internal energy for a material as the sum of all the kinetic energies of the particles plus the sum of all the potential energies of the particles within a material. Internal energy, like all energy, is conserved. It can't be created or destroyed, but it can be received, it can be given away, it can be gained, it can be lost. Internal energy is a confounding concept in Year 11 physics. We don't attempt to put a number on the internal energy, that's much too difficult. We couldn't possibly calculate the sum of all the kinetic energies and the potential energies between the particles. It still remains a useful concept, however, as it allows us to think of the energy within a material as a well or a resource that can be accessed through the different modes of heat transfer. In thermodynamics, each particle within a material is said to have kinetic energy, which is linked to its mass and its motion. You may remember from your Year 10 studies the equation EK, kinetic energy, is equal to a half mv squared. In thermodynamics, each particle within a material is also said to have potential energy. Potential energy is the energy of the particles due to their location and attraction to each other. Potential energy is greater when the particles on average have greater distances between them. Potential energy is lower when the particles on average have lower distances between them. As stated previously, temperature is a scale that allows us to communicate and compare the hotness and the coldness of different substances. Temperature is linked to the kinetic energies of the particles within a substance. In thermodynamics, we say temperature is a representation of the average kinetic energies of the particles within a material. A teaspoon of boiling water would have a very high average kinetic energy for the particles within it, whereas an Olympic-sized pool would have a much lower average kinetic energy for the particles within it, even though there are a great number more of those particles. This understanding of temperature shows why Kelvin as a scale is preferable to degrees Celsius. Ice stored in a freezer might be at -5 degrees Celsius. This negative value might suggest incorrectly that the average kinetic energy of the particles in the ice is negative. Kelvin, being an absolute scale, has no negative values. In Kelvin, the ice will be thought of as 268 Kelvin. Thermal energy. Thermal energy is a term which is loosely linked to internal energy. It can be thought of as the energy within a material due to the motion and relative spacing of the particles of the material. Heat. Heat is best thought of as the flow of thermal energy. You may remember in Year 8 thinking that heat was the energy inside of materials, a type of potential energy within a material. In Year 11, we think of the internal energy within a material due to the motion of its particles as thermal energy, and we keep this separate from our understanding of heat. Heat, for us in Year 11, is the flow from object to object, across boundaries, or from place to place, the flow of thermal energy. In Year 11 Physics, we give heat the symbol Q, that is capital Q. And we say that for a substance, capital Q is greater than 0 when the thermal energy is received, and we say that capital Q, heat, is less than 0 when the thermal energy is released by the substance. Work. Work is a term that you should be familiar with from your Year 10 science studies and also from your Year 8 science studies. We think of work as transforming energy from type to type, place to place, or object to object. In Year 10, we think of work as force multiplied by displacement. Work as an idea is important for us in thermal physics because thermal energy within a material can do work on the world around it, and at the same time, the world outside can do work on thermal energy within a material. So, while we might say that internal energy is too difficult to measure, in Year 11 Physics and Thermodynamics, we're very comfortable with measuring the change in internal energy. We say that the internal energy of a material changes when heat is released or absorbed by the material, or when work is done on the material or by the material. We'll cover this idea, delta U equals Q plus W, later in our studies of thermodynamics. So that's the end of another video. So what do we do now? Take a moment to jot down the ideas from this video in your physics notebook. Try to do it from memory, don't go back and just copy things out. Read and take notes of Chapter 1.1 of the Pearson Physics text. Complete Chapter 1.1, Heat and Temperature Questions from the Pearson Physics text, and complete the Exploring Physics Problem Set 1, EPPS 1. Once you've done all of that, you'll be ready to do the exit ticket for Lesson 3, Heat and Temperature. I hope this was useful.